Hello everybody, this is video 16.2. We're going to be looking at counting the number of outcomes. As you would imagine from video 16.2, we're going to need a lot of 16.1. So make sure that you watched that video, read that section of the book, maybe both, that you've got any questions answered from that section before moving on as much as possible, as best as possible. So let's get started. So in 16.1, we talked about experiments that just had one outcome. Just one thing was occurring. We were rolling a die and we were trying to get a 2 or trying to get a 4. Now we're going to have things where there's more than one thing occurring. So as an example, we might be rolling a die and flipping a coin. And so now we want to know the probability that we get an even number and heads, or that we get something less than 4 and a tails. So there's more than one thing happening at one time. We need this and this to occur. And we'll talk a little bit more later on about the difference between ands and ors. But for right now, what we're talking about, we need both things to occur. We need the first outcome and this outcome, second outcome, and potentially a third, fourth, fifth, however many other outcomes we need. Now, when we have a sample space that's made up of these multi-stage experiments, then we're going to have what's called compound events. And so this is where we're going to have more than one thing happening at a time, as opposed to a simple or uniform event that we looked at in the previous section. Now, I want you to be very careful about this because the assumption might be that if I'm rolling 2 dice, that this becomes a multi-stage experiment. And it might be. We certainly could set it up that way where if I have a red die and a blue die and I roll both of them and I want to know what's the probability that I get a 2 on the red die and an odd number on the blue die. So I could have something, crazy like that. But most of the time when we're rolling 2 dice, like in a game, we take the top numbers and we add them together. So if I roll a 4 and a 3, I don't really think about the 4 and the 3 as much as I think of the 7. So in that case, even though I have two sort of apparatuses working, I'm only getting one result. I'm only getting one thing. And so the same thing could be true if I have a number on a spinner and a number from a die. Even though I have two things, I might just be adding that result and just getting one number. In that case, it's not really a multi-stage experiment because I don't have more than one number being produced. I still have the one outcome. I've got more than one thing producing that outcome, but think about what you would write. On the next slide, we'll look at this in a little bit more detail and hopefully it'll make a little bit more sense. But don't think just because we're using more than one thing, like more than one spinner or more than one die or a die and a spinner and whatever else, that makes it automatically multi-stage. Being multi-stage is more about the type of result that we get or the type of outcome that we get more than the number of pieces or toys or whatever that we're using to get that thing. So let's look at this example where we've got a six-sided die, a fair six-sided die, and this spinner. So we've got this die and this spinner. So we could record these in what we call an ordered pair. And you may have seen this idea of an ordered pair before if you've done any sort of like graphing, where the point 1, 2 is not the same as the point 2, 1. They're located on different spots when we graph. So in this case, we're going to put the number that we get from the die as the first number, and the number we get from the spinner as the second number. And I just chose that ordering because that's how they're shown in this picture, the die and then the spinner. So if we're going to record our data this way, notice that we could get 6, 2. That would be a 6 on the die and the 2 on the spinner. But we couldn't get 2, 6, because although I could roll a 2 on the die, there's no way for me to spin a 6 on that spinner. And so that's why we call this an ordered pair, because the order makes a big difference. When you see numbers in parentheses like that, the parentheses typically mean these are ordered. These have to be in this order. When they're in sort of the curly braces then that we use for writing sets, that means we can move these in any order that we want. So just if you've ever been curious about the difference between the parentheses and the curly squiggly things, that's the mathematical distinction between the two. Now, we want to look at this question of how many outcomes are possible. One way we could do this would be to just simply write out all the outcomes. So roll a 1, spin a 1, roll a 1, spin a 2, roll a 1, spin a 3. We could do that, but hopefully you and your students are going to recognize that's kind of a waste of time. There's an orderly way to do it, what's called the odometer approach, that you start with just 1 on the die and then go through everything on the spinner. Now go to 2 on the die, do everything on the spinner. Go to 3 on the die, do everything on the spinner. So there is an orderly way in which we can do it, but there's going to be a lot of outcomes. And so by starting with something that we can do but seems really just sort of unwieldy to do, hopefully that motivates students to want to find a more efficient mathematical way of approaching this problem. Is there a simpler way to doing it? And of course there is. So we want to know how many outcomes are possible, or to use the language from 16.1, what is the size of our sample space? Once you know the size of the sample space, that helps to start to find the probability, because then we can just look at the size of the event, and then we can start to calculate probabilities from that. So a good starting point for this is going to be using what we call a tree diagram. And you may have seen tree diagrams in other classes before, but this is a tree diagram for a much smaller multi-stage experiment. We've got 2 spinners. They don't seem like the most interesting spinners in the world, but they're nice and small, which is good because it keeps the tree diagram nice and small. We got 1 spinner that'll spin a 3 or a 4. Now, we don't know anything about the probabilities necessarily. The 3 section might be huge. The 4 section might be huge. We don't know. So we don't want to necessarily assume that these are equally likely outcomes. We just know that these are the only 2 outcomes. We have another spinner that is blue and yellow. Now, it's also possible that the first spinner and the second spinner might be the exact same spinner. The 3 might be blue and the 4 might be yellow. And so we're using the exact same spinner twice, but we're recording different data. The first spin, we're recording the number, and the second spin, we're recording the color. So again, we don't want to make a ton of assumptions about what these look like, but they might just be 2 different spinners, where one is just a black and white spinner that has 3 and 4, and the second spinner might not have any numbers at all. It just might be the 2 colors, blue and yellow. But in any event, we're going to get these possible outcomes. And so we can see the first spinner, we've got our outcomes of 3 and 4. Let me get the pen working here. So we've got 3 and 4. And then the second spinner, we've got our 2 colors. And we can see here, we've got our ordered pairs. And I'll put the parentheses in so they look like ordered pairs. And now we can count. There's 1, 2, 3, 4 possible outcomes. Now, we can also do this by looking at the size. Let me switch to black here. So the size of the sample space. So the size of the sample space of the first spinner is 2. And the size of the sample space of the second spinner is also 2. Now this can be a little confusing for some students, because they'll look at this and they'll think that there's 4 possible outcomes. And you have to take a moment to sort of draw this line and show them, no, it's just 2. These 2 have been repeated, because if I spin a 3, I can then get a blue or a yellow. If I spin a 4, then I can also get a blue or a yellow. And so it's not that there's 4 outcomes here, it's that there's 2 outcomes on the second spinner for each of the 2 outcomes of the first spinner. I've found that sometimes it helps to draw this not in this horizontal way, but in a vertical way like this. So here's the 3 and here's the 4, with a lot of space in between. So I could get a 3 on the first spinner, and then what could happen on the second spinner? I could get blue and I could get yellow. Now let's look at the other case. If I spin a 4 on the first spinner, then what could I get on the second spinner? And now as I start to separate these out, literally, students start to separate these out sort of cognitively, that the blue and the yellow here and the blue and the yellow here are very different outcomes. And I can go through and count 1, 2, 3, 4. So by constructing this tree diagram, it gives us a way to start to move toward this calculation step that it's the number of outcomes here, 2, and the number of outcomes here, 2, and so 2 times 2 gives me 4 possible outcomes. It's really important that students understand where this multiplication comes from. You don't want to just tell students, okay, to find the size, let's just multiply all the numbers together. The let's just multiply things together approach is going to lead them astray very quickly. We saw in 16.1 there are times where we add these things together, and then we see now in 16.2 there's times where we multiply these things together. And again, we'll get into a little bit more detail about when to do which, but if we look at this tree diagram, the multiplication stems from this very naturally. We understand where the multiplication comes from. So we're looking at the concrete model first, and that's motivating the abstraction into the multiplication rather than starting with the abstraction of the multiplication and not having it connected to or rooted in anything. It's just multiplication because I tell you to do multiplication. And that's the sort of thinking and teaching that we want to try to avoid. So let's go back to this problem. Now that we've looked at this tree diagram, we should be able to think of how we could construct how many outcomes we have here. So we've got 6 outcomes on the die, and we've got 4 outcomes on the spinner. So if we wanted to start drawing our tree diagram, we'll start at the beginning. And so we've got a 1 on the die. And so now if I roll a 1 on the die, what could I get on the spinner? Well, I could get a 1, a 2, a 3, or a 4. Well, now let's look at the die. We could also get a 2, and that gives us a 1, a 2, a 3, and a 4. And then we could also get a 3. I'm not going to go through all these, but hopefully students start to notice a little bit of a pattern that for every outcome on the die, I have 4 outcomes on the spinner. For every outcome on the die, I've got 4 outcomes on the spinner. So how many outcomes do I have on the die? 6. And each one of those gives me 4 outcomes on the spinner. If you need an intermediate step to this, you can also show, here's my 6 outcomes on the die. Well, I know there's 4 outcomes here, there's 4 outcomes here, 4 here, 4 here, 4 here, and 4 here. Like we said, for every die outcome, there are 4 spinner outcomes. And so now I can just put a 4 underneath each of these die outcomes, and hopefully students know multiplication well enough to recognize that when I'm adding 6 4s, that means I'm doing 6 times 4. And so I'm going to have 24 possible outcomes here. Now, it doesn't mean that they're all equally likely necessarily. In this case, they are. But there's going to be cases, again, like we talked about, where the spinner is not necessarily divided uniformly or not divided equally, so the probabilities won't be uniformly distributed. So for right now, we're just counting the number of ways that something can occur, the possible size, the sample space, but we're not necessarily making a connection to probability yet. We're getting there. But for right now, we're just counting how many things are possible. So this last topic is a little bit advanced, but we're going to talk about it just a little bit. We're not going to get too far into this, but it is important that we talk about it at least a little bit. And this is the idea of dependent outcomes. We talked before about how the coin, the die, the roulette wheel, how they don't have memory. And what's happened in the past doesn't impact or change what's going to happen in the future or happen in the present even. If I flip that coin a million times and get heads a million times, again, the probability of that next heads, still 1/2, still 50%. The fact that it's happened so many times in the past doesn't change what's going to happen next. A dependent outcome is the opposite. It's the opposite of that. This is where what's happened in the past very much changes what's going to happen next. So as an example here, we have this thing called a polya jar or a polya urn, and the name comes from this Hungarian mathematician, George Polya. And so let's take this jar here, and let's say that we've got inside 10 red marbles, 10 blue marbles and 10 green marbles. So what is the probability that I draw a red marble? Drawing blindly, not looking into the jar and like specifically grabbing for a red marble. So the probability that I draw a red marble on my first pull is going to be 10 out of 30. Why? Well, because there's 10 red marbles. And so I know that my event in this case is going to be each of the 10 red marbles. So there's 10 ways I can satisfy this event. The sample space in this case is 30 because there's 30 marbles. So there's 10 out of 30 marbles that I can draw. But what happens if after I pull out that first red marble, I don't put it back? I leave it off to the side of the jar. And so now I want to pull out a second red marble. Well, now things have changed because I don't have 10 red marbles anymore. Now I just have 9 because I took one out. And I don't have 30 marbles anymore because, well, I took one out. And so now this probability has become 9 out of 29. So the probability of drawing a red is going to depend on what's happened in the past. If I drew a red marble and left it out, this probability changes. The probability of drawing the third red marble after these two events is going to be 8 out of 28. And so now the probabilities are going to be dependent on what's happened in the past. If the first marble was a blue, so we'll look at another experiment here. The probability of the first one being blue would be 10 out of 30. But now the probability of the second one being red, if the first one was blue, is going to be 10 out of 29 in this case. So you can see that the probability of drawing a second red is going to be dependent on what the first marble was. If it was red, we got 9 out of 29. If it wasn't red, we got 10 out of 29. Again, this is a little bit more advanced, right? But we can think about how to present ideas like this so students can see the difference between independent events, where the probability is independent of what's happened before, and dependent events, where things are very much dependent on what's happened before. I also want to mention very quickly that this Georges Polya, you may come up with this name again later on because he wrote a very famous book called How to Solve It. It's a book about problem solving and how people think about constructing methods of problem solving. If you're really interested in math education, it's definitely a book worth reading. I'll warn you, it's really old. I mean, it's over 100 years old at this point, I believe. So some of his writing, some students have found to be sort of not very in tune with sort of like contemporary society. He uses a lot of masculine pronouns. He very much assumes that everyone who's a mathematician is a male. And so we used to read this in my methods class. Some students got really sort of annoyed with the language. It's definitely, you have to read it through the lens of knowing when it was written. If you can get past that, there's a lot of really good mathematical pedagogical thought in there. If that's going to be a barrier for you, then maybe not worth looking at. But from a mathematical pedagogical perspective, very good. From a sociological perspective, probably not as great. But take that for what it's worth. Okay, so for your checkpoint problem, I want you to think about how you could construct a multi-stage experiment with 12 different outcomes. So we looked at one that has 4, and we looked at one that has 24. So can you think of a way to do it where it would have 12? Now, I'm going to ask you not to do anything silly like a spinner with 12 different areas and then a spinner with just one area. Like that's not very creative. So I want you to think about ways you could get 12 different outcomes. And then once you've come up with one, challenge yourself to see if you can think of another one that's different, a second way to do it. So, get as much detail as you want into it, but see if you can think of a way that you can conduct a multi-stage experiment that has 12 different outcomes. If you have any questions about anything from this video, by all means, please bring them to class. We'll get your questions answered. All right, thanks.